Hello, everyone. Welcome back to SAT Math Question of the Day. Here's our question of the day. Please read it, pause it, try it yourself, come back, and we'll try to show different approaches on how to do it. Okay, so you have someone's auto yard is filled to capacity with only cars. When it is filled with only cars, it has 60 cars. When it's filled to capacity with vans, it has only 50 vans. Oh, this is the trade-off problem. Which linear equation models the number of cars in the vans that can be in Lynn's yard when it is filled to capacity? Right. Yeah. So those are all the, in other words, you have like this is the trade-off problem. It goes AX plus BY is equal to C. That's sort of the form of this type of trade-off.
Okay, how is it a trade-off?
Oh, it's a trade-off because you can have both cars and vans, but you can only have 60 cars and you can only have 50 vans. But if you have 40 cars, then you can have a certain number of vans. See, if you have 40 cars, then you can have a certain number of vans. So
the AX has something to do with the cars, right?
Well, first
And
we have to
BY
define
has something to do with the vans.
Wait.
Right. So how are they being traded off? AX appears positively and BY appears positively.
Yeah,
a trade-off is that if you fill it with cars, then you don't have vans. And if you fill it with vans, you have less capacity for cars. So why do you add them?
That's because C is a constant. C is a constant. It's this.
Well, I'm not talking about C. I'm talking about the plus. You're adding the. If you have more cars, you have fewer vans.
Exactly.
And if you have more vans, you have fewer cars.
Exactly.
So shouldn't there be a minus sign?
No, there isn't a minus sign because the C stays the same. Usually,
well, the C. So who cares? Maybe the lot gets bigger when it's hotter.
Seth,
the C gets bigger
when it's
hotter. And smaller when it's colder.
Look, the trade-off problem is classic. You have 200 people, right? And you have to fit them in tables where there's a 5-person tables and 10-person tables, right? So X are the number of 5-person tables, Y are the number of 10-person tables, and you have to seat 200 people. So it's a trade-off between the 5-person tables and the 10-person tables. It's a classic trade-off problem, isn't it? You're just giving me a hard time.
I think what you're missing is wondering what happens if you're trading off the things counted by X against the things counted by Y, which means what happens if you make X bigger?
Wait, don't talk about X and C.
X and Y are variables, right? They're the things being traded off against each other.
Yeah.
Let me ask you, Joel.
Okay.
What if X is made bigger? What happens to Y?
Seth, can we do a favor? Can we talk C and V?
All right. What if C is made bigger? What happens to D?
V. V would have to be made smaller.
Oh. Okay. I think we should point that out to our audience right away. Okay. The trade-off is that when C and V are such that the lot is filled with capacity, whenever you make C larger, to keep the lot filled to capacity, you make V smaller.
Right.
And if you make V smaller, then you make C larger.
Right.
Even though the equation says you add them.
That's right. Yeah.
Right?
Yeah.
So what I think people need to realize is that when you express a trade-off, you don't write an equation that says that there's a negative.
Right. Okay.
You actually add the things together to form the constraint.
Right.
And so what led me to the solution right away is that when the thing is filled to capacity with cars, C is 60. That
Right.
C becomes 60.
Right.
And the left-hand fraction becomes 1.
Right.
The equation says that the left-hand fraction plus the right-hand fraction added together equals 1.
Right.
And so when C equals 60, V has to be 0.
Right.
And then on the other hand, when C is 60, V equals 0.
Right.
And when V is 50,
Yep.
then C has to be 0.
Right.
See? So that leads so seeing the 60 here and the C over 60 here and the 50 there, the 50 there and the V over 50 here added together equals 100%
Right.
of the capacity. That leads the eye to realize that A is the answer.
Right.
And the solution is done.
Right. So I didn't have a chance to actually solve it myself. Seth did it, so I can't really say how I would have done it, because I never went past mentioning what type of problem it was. Good job, Seth. Yeah, I mean, you can definitely throw out this one because C and 50 have nothing to do with each other, and C and 50 have nothing to do with each other. So
they flipped it around.
This is there for people like myself who may have dyslexia or get confused with the numbers and mess things up.
Wow.
So you got to be careful.
Well, let's see. If we write the equation, the correct equation, C divided by 60 plus V divided by 50 equals 1.
Right.
And we clear the fractions. You multiply the whole thing by 50 times 60.
Right.
What you'll get is 50 times C plus 60 V equals 50 times 60.
Which is 300. Which is 3,000.
Which is 3,000. Yeah. So this is the trade-off equation is equivalent to this equation where the coefficient of C, the number of cars, is 50, the number of vans. Right.
Yeah. Oh, I see. Right? So this isn't nonsense.
So this is wrong. This answer. This is a distractor. It's wrong, but it would be correct. It would be right if they replaced the one by 3,000.
You're right. Now, if they gave an easier problem, the easier way to formulate this would have been the way with the people problem. They would say a yard can handle 3,000 cars, and the yard can handle 3,000 cars.
But the thing is, you can't have a constant on one. So the thing is, you need to write it so that again, the trade-off is not the number of cars that the lot could hold. The trade-off is between the number of cars in the lot,
right,
traded off against the number of vans in the lot.
Right. So let me just work it out myself. If there were if the lot can handle 300 cars, and it only cars and vans combined, and the cars are 0.
Wait. Hold on. You wrote 3,000. 3,000. You wrow 3,000.
Vehicles. Sorry. Vehicles.
No. 3,000 is number of cars times the number of vans.
No. It can't be the number of cars. What? 300?
It is. It's the maximum number of cars times the maximum number of vans.
Oh, you're right.
Yes, I'm right.
Wait. Hold on. So, wait. If cars are 0, if cars are 0, then vans have to be 50. Right.
Yes,
Okay.
that's right. Yes, indeed. Yes.
Oh,
That is how it works.
Oh, and cars. Wow. So 3,000 is that is a little bit confusing. So it's a little bit different from the table setting problem where you have 200 people. But it feels like the same
the table setting. Yeah, it is. Yes, indeed. Here you're talking about figuring out the capacity when the number of tables affects the capacity by multiplying the number of people who could be on a table.
Right.
So if you say, but here the units are not like people, like size per unit of capacity. You're not talking about packing the lot with
elevators, like elevators that can
yeah.
handle 3 cars, and elevators that can handle 5 cars. Right?
Yeah.
Okay, wow. So this is one of the harder questions we hit. The trade-off linear equation trade-off problem, it doesn't come up that much. Usually,
So you get y equals the approach that this problem leads us to is do not quickly guess that the problem is a standard problem that you may have heard of. The approach is read the question.
Right. Now,
and interpret what it says, and then fit it formula. One approach is to fit it to the proposed answers and see which one matches. One approach. The other approach is to translate the condition in the problem, the question in the problem, the constraint in the problem into math, and then see which distractor, see which choice fits your result.
Why don't we just stop talking about, it sounds, you're saying very theoretical. In terms of, like, let's say you don't realize it's a trade-off problem, or let's say you just come into it, you don't really even understand it quite yet. You could just see which equation works, just which one works. And only one works, right? You know which one works. Like when C is 60, V has to be 0. And just test it. See which one. See which one works, right? And the only one that works is A. Isn't that correct?
Yeah,
right? Isn't that
now, there's something missing in this problem. The thing is,
that's all you do. Test which one works. Come to think of it, the approach that probably makes the most sense, I would think, is just test to see which one works.
Yeah.
Right?
So the problem is about it being filled, is what are the conditions, what they could be when it's filled to capacity. Right? Now, here's a problem. You could satisfy the equation where C and V are not whole numbers.
Okay. So, yeah.
That's ridiculous.
Oh.
Unless you're, well, it's an auto yard. Maybe it's a junkyard where you would cut a car in half.
But I mean, this equation could be solved. Let's say you do 30 over 60 plus 25 over 50 equals 1. That's a good solution to the equation.
But take it's the same thing. What you could do is
I see. You could do 40 over 60.
Make 30 a little bit bigger, and then make 25 a little bit smaller.
Yeah, but if you make it like 40 over 60, then you have a problem.
Because you could do 30. Say 30 plus a half over 60,
right?
Plus 25 minus some little fraction over 50 equals 1.
Oh, I see. So that would work.
And you figure out the little question mark is.
Well, no.
So the little question mark is whatever it takes to be question mark over 50.
Seth, you're making it too complicated. Come on.
Should be 1 over 60. Therefore, question mark is 5/6.
Yeah.
So if you could add half of a car if you take away 5/6 of a van.
Seth. Why don't you look at the way I did? It's easier to see. You have 40. 40 is C, right? 40 is C, so this is a 4. 40C makes 2/3, right? So in order to add to 1, B over 3 has to be a third. In order for B over 3 that has to be a third, B has to be 50 over 3, which is impossible.
Yeah.
Okay. So that's an easier way to see it, rather than this weird stuff you wrote.
Yeah. Another thing, so what they should do is also put in the condition that C and V have to be natural numbers, including 0.
Right. Yeah. Right. Exactly. Okay. Today's Throwback Thursday. We better move on.
Yeah. Okay. Let's see how they explain it.
This is a really interesting problem to see how they did it. I'm going to vote for my suggestion on a problem like this. After going through all the approaches, is just do the one I think I did at the end. Just test which one works. Only one of the equations works. Use some common sense. When C is 60, V has to be 0.
Yeah.
So let's see how they do it. It'd be interesting to see. This is not an obvious, easy problem to sort of figure out. And you have multiple approaches to it. Mm-hmm. Okay, and essentially that's what Seth did. Seth just saw which one worked. Okay, let's see. Mm-hmm. Okay, how did we answer it? Okay, 4 steps. Okay, all the answer choices are of that form. That's a good observation. This equation relates C and V when the yard is filled to capacity. In fact, AC represents the fraction of the yard that's filled with cars, and BV represents the fraction of the yard when filled with vans. And 1, or 100%, represents the full yard. When the auto yard is filled to capacity with cars V is 0, then it has 60 cars. Since the yard is filled to capacity, we can plug these values into our equation. Aha! Oh, that's interesting.
Yeah.
But this method, they're solving for A and B. It's a lot slower than just testing. But this method requires you to understand this formulation, which may not be at all obvious and is certainly not a classic y equals mx plus b linear equation word problem. Oh, I see. It says all the choices are of that form. Oh, I see. So it's just, I see. It's telling you, hey, all the answers have to be of this form. I see.
Yeah. Well, I want to point to people. Let's see. Where's the final answer? Let's go to. Good. Let's concentrate on.
Okay. Go ahead.
Now, could you bring it up? Bring it up so I could scribble on it.
What? Let me see if I can do this. Oh, look at that. Oh, no, that doesn't work. Wait, hold on. No. Okay, that gives you a little bit more stuff. Is that okay?
No, please give me the one where the 50 and the 60 are in the denominators.
Yeah.
Yeah, good. Now, I want to point out.
Go ahead.
Pete, look at the bottom of the page.
Got it.
If you plot the solutions to this equation, what do you get? Well, when let's fill in the axes. Let's say this is the C axis and this is the V axis. When C is equal to 60, right? Then V is equal to 0.
Right. That's right.
And when V is equal to 50,
Right.
then C is equal
Yeah,
to
that's the
0.
classic trade-off. The trade-off problem graphs is a triangle. A slanted line with negative slope.
It's a slanted line with negative
Negative slope,
slope,
right? But
and this
connects
is
the
what's
two.
called, this is this is the form of the line when drawn this way. This is called writing the form, writing the line in 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 intercept form,
Absolutely right. That's right. That's
where
classic
if
for
you
a trade-off
know
problem.
the x and y
That's right.
intercepts,
Right. Yeah.
this is the intercept form
Yep.
of the line.
Right. Yeah.
And it's handy to see, it's handy to realize how it works. That the intercepts are first. They critical concept is the points are on the line when the coordinates satisfy the equation. The intercepts are points where one of the coordinates is 0. And the particular intercept is the value of the other coordinate.
Right. Yeah, it's the
Okay?
extremes. It's maxing out on one or maxing out on the other.
So the trade. So there's the. So notice that that's in general. Here's the thing about equations of line. If you have an equation of a line, if A and B are both positive, the slope is negative.
That's right.
Okay.
Yeah.
And that negative slope, therefore, indeed represents the trade-off. The trade-off
Exactly.
is that if this goes up,
Then y
the
has
x
to go down.
value goes up.
That's right.
Then the y value goes down.
Exactly. So the approach we're doing is we're just killing this problem to death by giving you different lenses, different viewpoints of the same problem. And that's really helpful in a math problem, is to view it from different aspects. Exactly.
Yeah.
Great. Okay, should we move on to our...
Yes.
Okay, so today's Thursday. Boy, this week went pretty fast. And on Thursday we do Throwback Thursday. So we go back about 20 years for SAT problems where some of them were more of a IQ logic type of reasoning type test. So here we have our Thursday throwback question of the day. I think I don't like to look at them ahead of time, but I can tell you already, I think Seth's going to have to do more of this one than me. I would probably use brute force. Okay. Oh, should we introduce ourselves? Why not? Let's do it first. Hey, this is Seth Chaiken. He is a PhD in math from MIT. He's Professor Emeritus in University of Albany. I'm Joel, as his brother, PhD in mechanical engineering. We're here to show you how to approach studying for the Math SAT, which is basically go to Khan Academy, and also also how to do specific math problems, which we just did. Okay, here's our throwback Thursday question. Notice you probably would never see this question on a post 2016 SAT, including the new digital ones that they're planning. Okay, if K and J are integers, integers could be any negative like whole number and 0. I'm planning positive whole number, of course. Like 5, 6, 7, negative 30, 0, or negative 100. If J and K are integers and J plus K is equal to 2J plus 4, we can solve for J. We could subtract 2J on both sides, can't we? So isn't that really negative J plus K is equal to 4? Right? Isn't that right? Did I make a mistake? Negative J plus K is 4. Okay, negative J plus K is 4. Or how about just K minus J is 4? Oh, look at that. K minus J is 4 is all the time. So obviously 3 is so we could... So there, that we throw out. So the answer is either... Wait. Yeah, the answer is either D or E. So we know that already. Okay, now, Wait.
Okay.
J is
Read
even.
my scribbling. I explained it.
Wait.
I put the answer on there.
But J, who says? Who says that J is even? J and K can be any integer we want. If you have this constraint, J and K.
No,
can
they
be
have to add up to two. Oh, yeah, I guess so. Huh. Oh, okay. Let's check. So certainly J and K. Yeah. Oh, I'm sorry.
Wait, K minus J has
Something
to
is
equal
it's
4.
the problem is I thought that this quantity here was this J was another letter.
What?
Yeah, I
Oh my
realized that.
God.
Okay, all
Wait,
right, good enough.
wait,
Oh
wait,
well.
wait, wait, wait. K minus J is equal to 4. So does J have to be even? I don't know.
No,
You can get any two numbers
no.
that subtract to
Wrong.
4. How about
Ah!
25 minus 21 is
No,
4?
that's why. No, okay. Do the math.
21 minus
Don't do
21
this.
is 4. How about this one?
Don't do this.
21 minus 17 is
J
4.
plus K equals 2J plus 4, right? So you could simplify this by subtracting 2J from both
That's
sides.
right. Yeah.
And you get, therefore, minus J plus K equals 4, which in terms of parity, this is just like adding. Right, the two numbers J and K, when combined by adding or subtracting, have to be a multiple of 4. Right.
What do you mean a multiple?
So one, if one is so they might both be even, but if you increase each one by 1, they still add up to 4, and they're both odd. So they might both be even. They might both be odd. But if one is even and the other is odd, then the sum is odd.
Right.
So they have to have the same parity.
Right.
Right.
Okay.
Which means that their difference is even. So 3 is the answer.
Right. Now Steph talked all this number theory stuff, but the way I did it as an engineer, mechanical engineering is my area. I mean engineering. I just realized that K minus J is 4. So then what do you do here? First of all, you throw these out because K minus J is even. And then you see, okay, does K and J have to be even? Well, let's try some odd numbers. Look, 25 minus 21 is equal to 4. That's cool. So it doesn't have to be even. Yeah, so it's 3. We don't have, in the book we only have the answer, which we're not going to check because I think we're pretty confident. Which I know we probably shouldn't do, but we're going to do it anyway.
Well,
we don't know how the SAT people did it because the book doesn't explain how to do the problems. They just give you the answers. So
I think my original argument, is still correct. Still correct, because my argument is that J plus K is even, right? Even though it depends on J,
right?
It's not constant. So if I say changed J and K, since the right hand side, if you change J to another integer, the right-hand side is still even. So whatever J and K are, their sum is even.
Right.
Which means that they have the same parity. And then again, if you change one of them, make it odd, then their sum is not even. So you can't do that. And therefore, that's still. So you could solve this problem even by ignoring that the J appears here.
Got it. So in other words, you're saying here you read it as J plus K is an even number. That's
I just read J plus K is 2 times something.
Yeah, J plus K is.
That's all you need to know.
So Seth basically said, we'll do it in like big black. Now over here. Well, that's just erase clear all the lines. Seth basically said J plus K is even. Okay. So if J plus K is even, then the only answer is 3. That's what it says. Okay,
Yeah.
great. Okay, so that closes our Throwback Thursday Throwback Thursday question. And if you have any, please give us comments on our YouTube videos. And if you have any SAT math questions, please email them to us at satmathquestion.
All right. Let me just say a number. All even numbers have the form 2 times some integer.
Right. Okay. Okay. Yeah, that's good. That's a very good thing to know.
Yeah, not so, which is when kids are first taught about even numbers, they're taught that a number is even when it could be expressed as the same number added to itself.
Right? I don't know.
And then you learn in algebra that for any number symbolized by a letter, the sum of the number added to itself is letter plus letter. And in algebra, that is equivalent to 2 times
m.
M.
Yeah.
And then in arithmetic, the meaning of multiplication, integer multiplication is, multiplied by 2 means you add the number with itself 2 times.
Right. Okay.
Like 3 times a number is gotten by taking the number and adding 3 copies of it.
Right. So it's 3x.
Like 15 times a number.
Okay.
Is take the number and add up 15 copies.
Okay. Enough. By the way, yesterday, let's. Sometimes we have a very, very quick session. We're not going to talk much about this, but we're going to feed the Seth a problem. Ready to feed the Seth? Have you ever heard of the 4 fours problem? To express the 4 fours problem. Express
4
the numbers.
fours?
Yeah, have you heard of this problem?
The 4 fours?
Yeah, have you heard of it?
No.
The 4 fours problem is a parent called me the other day. Apparently, they introduced this in 7th grade. And I'm not sure exactly how they did it in 7th grade, like what level they did it on. But the 4 fours problem, look it up. It's try to express the numbers 1 through 20 with 4 fours.
Oh, 4 fours. Oh,
right, okay, and you could use all sorts of operations, but it turns out the answers depend on which operations you choose.
Of course.
So, anyway, okay, I just wanted to know. We're not going to do it. We're not going to do it, but have you heard of it?
It's kind of tedious.
Yeah, and then
do you have to use exactly 4 fours in each expression?
Right.
Or could you use other smaller numbers of 4s?
No, you have to use 4 fours. Like 2 would be 4 over 4 plus 4 over 4, which would be 1 plus 1 is 2. Now, there are different versions of it. Sometimes you're allowed to use the factorial sign. Sometimes you're allowed to concatenate. Okay? Concatenate
you get
means
44?
You can use 44, right? Maybe 44 divided by 44 is equal to 1. So that's called using concatenating them.
So if you want to write 4, that to say 4 equals 4. Use 1 4. That's no good.
Right, that's no good. But it turns out
if you use 4 fours to write the 4.
But it turns out that if you, first of all, I think the answer depends on what conditions you use. Some of them on the internet allow you to use factorial. Some of them allow you to use concatenation. But there are generalizations to this problem, which make it even more interesting. Like you could look up on the internet the generalizations of the 4 fours problem. So can you take any number of integers and express other integers in terms of other? Anyway, actually, it's the beginning of a whole thing.
Yeah.
So anyway, so it's interesting about math, right? You have a little silly problem, and you can try to generalize it and make it even more complicated,
Yeah.
give you more
Yeah.
understanding of number theory. So anyway, okay, no, sort of curious. You never heard of it, but look it
No,
up on the internet. Yeah, you'll
no.
see.
Well, yeah, there are. I've heard of problems in the same spirit.
Yeah, yeah,
One interesting problem is that if you have several numbers, right, whose greatest common divisor is 1, right? Well, then you could form 1 by combining these numbers with addition or subtraction with coefficients, right? But and so any number, because we're talking about whole numbers, we're talking about integers. You have numbers, greatest common divisor is 1. There's no common factor except for 1. 1 isn't a factor. Any integer can be expressed as a integral combination of these numbers. But not every integer can be expressed as a positive integer combination of the others. But large enough numbers can all be expressed as a positive combination of them.
Oh, interesting. Okay.
So the idea is, which numbers can you not express?
Yeah. So that's so much more complicated than this.
Like 7 and 11.
Yeah.
Right. You could get 7, and you can get 11. Right.
Yeah.
And you can get 18. 7 plus 11 is 18. You could get 14.
Yeah.
But you cannot get 15, 16, or 17.
Okay.
But at some point eventually you can get all the numbers.
It's so much more complicated. Okay, just
Yeah.
when I did this, I was thinking about it at night, and then I woke up and I realized this is completely cheating. Like 19 is not that easy to get using this, but apparently you have to use the factorial or concatenation. But I totally cheated stuff. So don't you agree that I just cheated? You could write it as 4 over 4 next to 4 over 4 is equal to 19 if you use this as base 18.
Oh, come on. Yeah.
That's totally cheating, right? I think that's cheating because I'm using...
Okay, math. One of the things in math is that when you start a problem, when you pose a problem, you state what the rules are.
Exactly. You have to state what the rules are. But I technically think this is wrong because I'm using the number 1 and 8 in order to say how to do it, right? See, right?
Yeah.
I'm saying the numbers 1 and 8, so I don't think this is the right answer. So I don't think I'm really allowed to do that.
Yeah.
But that works.
You can say it's base 4 over 4. 4 plus 4.
Yeah, but now I'm using too many 4s. If I say it's base 4 over 4, 4 plus 4, then I've used up my 4 4s, and I can't say 4 over 4 over 4 over 4 anymore, right?
Yeah.
So I've used up all my 4s. I've used up my 4 4s just telling everyone what the base is. So I don't think that was the right answer, but I learned from it. But
okay.
So anyway. Okay, 4 4's problem. If anyone's
enough,
interested, look it up on the internet. It's a pretty interesting problem. It's just because a lot of that Seth's right. When you do a problem, you have to know what you're allowed to do. You have to know the rules of the game. Well, I'm
just saying that. Not a matter of knowing. That's when somebody gives you a problem.
Right. Yeah.
But when you make up a problem,
Mm,
you can make up any rules you like.
right. So I can make up the problem that any base is involved. Then every number greater than 5, every number greater than 5 can be expressed as just 1, right? Because you can just make up any base you want. Make up base
Yes.
3,794.
Yes.
So, right?
Well, no, you could, 1 or 0, 0. No.
Yeah, you can make up any base you want, but then you have to say the
See,
numbers.
except how could you get 1? How could you express 1 with 2 ones in any
Right,
base?
then you have a problem on the downside below. No, but then you can flip to just say, well, that's just regular base. That's just regular base 10. Anyway, enough. But it's interesting. It's sort of an interesting problem. Anyway, okay, so I guess that's it for today, right?
That's it.
Okay, we're done.
Okay.
We are more than done. Okay,
You're
everyone.
more than done.
Take care.
More
Have a great
than
day.
done.
More than done. We're overdone. We're overcooked here. We're overdone. Definitely overdone. Okay, everyone. Have a great day.